density and therefore stratification in the ocean is driven by temperature, salinity, and pressure. But much of the stratification that we see throughout the oceans is actually due to temperature gradients. And so when we look at a temperature profile, so the temperature as a function of depth in the ocean, this is the governing, this is the primary factor that controls the vertical mixing and vertical properties of the ocean, and therefore has a large impact on the chemical distributions that are associated with these different vertical layers. So just to plot out what does the ocean vertical temperature structure look like? It depends where you are, of course, and it also depends when you are there, when you're looking, especially in regions that have high seasonality. So, but for example, in the high latitude oceans, for example, in the Southern Ocean down by Antarctica, we get pretty constant temperature profiles. And in fact, the temperature as a function of depth doesn't change much. So this might be an example of high latitude temperature profiles throughout the ocean. So this means that there's not actually a lot of stratification in these regions, and that's why we get these deep mixing events in the North Atlantic or the Southern Ocean, for example, where waters can easily overturn and mix down very deep in the ocean. As we move to the mid-latitudes, things start warming up, but the deeper waters are relatively similar to what they were in the high latitudes. So it might look something like this, and then we get this zone where temperatures start increasing. And if this is mid-latitude profile, we've got a few different components that are starting to come into play here. We've got this zone between maybe 500 and 1,000 or 2,000 meters, where there's relatively strong changes in temperature as a function of depth. And this is what we call the thermocline. And the thermocline, so as you go deeper through this layer, waters are getting colder, and as a result, they're also getting more dense. On top of that, we've got the surface, maybe mixed layer, or just the surface layer. Sorry about that. Surface mixed layer, anywhere from, 10 meters all the way down in some places, and sometimes as deep as 500 meters or so during strong mixing events. And this tends to vary based on seasonality. So in the winter, surface temperatures might be just above 10 degrees in the mid-latitudes, for example. And then in the summertime, we start to get stratification. And so what that means is that this surface layer above the thermocline actually increases in temperature. And so we get summer and winter differences in the upper surface layer. And this region here underneath this the summer is what's called the seasonal thermocline, whereas this is more of a permanent thermocline that doesn't change seasonally. So this one does as the surface temperatures increase. And then in the tropics, we've got an even different situation where it follows the same sort of pattern through the thermocline, but then we often start increasing temperatures, and those go up to 20 degrees or slightly more in the surface waters of the tropics. And that's and this doesn't, in the tropics, these temperatures don't fluctuate too much because there's not a lot of seasonality in the tropics, and so this thermocline remains relatively constant. In any case, the take-home message here is that the temperature is largely controlling the vertical stratification, and it depends on where you are in the ocean, what that vertical structure is, and how much of a gradient there is in temperature and therefore density. And as a result of that, we see chemical patterns in the oceans that follow these general patterns of temperature and physical properties.